This video is brought to you by the Environmental Protection Agency. The use of any trade names or commercial products does not constitute an endorsement on the part of the Environmental Protection Agency. For the arsenic rule, EPA evaluated several technologies as candidates for best available technology for arsenic removal, including modified coagulation filtration. Typically, coagulation filtration treatment uses the process of particle destabilization to remove colloidal and suspended matter from the water supply. This process results in the formation of flock particles that are removed by clarification and/or filtration. The coagulants that are commonly used are aluminum or iron salts that form particulates that attach to the suspended or colloidal matter. Increasingly, polymer aluminum-based blended chemicals are being used for the removal process. The installation of these conventional gravity coagulation filtration systems solely for arsenic treatment is generally uneconomical. However, the process of coagulation filtration can be modified to remove dissolved inorganic matter, including arsenic. Typically, if a source has arsenic-3, oxidation, usually chlorine, is used to convert arsenic-3 to arsenic-5. A coagulant in this case, ferric chloride, is added to be oxidized, producing iron hydroxide particles. The hydroxides in arsenic-laden water are held in a retention tank to allow the co-precipitation and adsorption process to occur. The arsenic and iron precipitates are filtered from the water, in this example by a pressure filter vessel. The filters are allowed to load with the precipitates until the filter is partially loaded, and then the filter is backwashed. The backwash waste is directed to either a sanitary sewer or dedicated waste system. Not many surface waters have elevated arsenic concentrations that are of a concern to public water supplies. However, the Yellowstone River, which originates in the volcanically active area of Yellowstone Park, is an exception. There are numerous public water systems that rely on the Yellowstone River as their source water and use coagulation filtration as their water treatment process. Two such systems are the City of Billings, Montana, and the Lockwood Water District. With the revised arsenic MCL looming in the future, the City of Billings began experimenting with coagulants other than alum to increase arsenic removal. Billings converted to ferric chloride as a coagulant.
Arsenic in the Yellowstone River, because it's a surface water source, is arsenic-5. Arsenic-5 is relatively easy to remove. Our treatment system here is a full conventional plant. We coagulate, flocculate, sedimentation, and then through filtration. We use a polyaluminum hydroxychloride, PACL, which is an alum blend, a proprietary alum blend. Prior to that, we used ferric chloride. Prior to that, we used alum. We went to ferric chloride because of our arsenic problems and when arsenic became an issue in the early 90s.
The Lockwood Water District continued to use alum as a coagulant. This provided an excellent full-scale comparison between aluminum and ferric-based coagulants.
We have treated with aluminum sulfate in the past and polymers that we use for that. Usually we got roughly 50% removal of the arsenic.
As seen on the graph, the Billings finished water arsenic concentration was consistently below the detection level, less than 2 micrograms per liter. In the Lockwood plant, alum removes significantly less of the arsenic. The City of Billings has since converted from ferric chloride to an aluminum polymer blend to reduce some corrosion problems attributed to ferric chloride. As long as the arsenic concentration in the Yellowstone River is less than 15 micrograms per liter, the polymer blended coagulant works for arsenic removal. If necessary, the city adds a small amount of ferric chloride to aid in removal of arsenic.
Our approach here is to also use ferric chloride. When we get above 8 micrograms per liter in our finished water, we start adding ferric chloride.
This is also being considered for Lockwood.
Right now, like I say, we are testing a polyaluminum hydroxide. We're not sure if that's the polymer of choice or the coagulant of choice. Right now we want to be able to feed a little bit of ferric to get rid of the arsenic, but we want to get that into some level that's more controllable for pH. But I would imagine that that's probably where we'll be 6 months from now.
Both the City of Billings and Lockwood Water District have tested the sludge. Neither demonstrated hazardous waste characteristics.
We've tested for the arsenic levels. The sludge processes that we use, sending out to a sludge drying pond, have that tested for metals content, and it's showing that we can land apply that. So to this point, we haven't had a problem with land application instead of having to take it to a landfill.
We have T-clipped that sludge. The TCLP test to date has been non-detect on arsenic.
Climax, Minnesota is also using coagulation filtration to remove arsenic. This system is participating in the United States Environmental Protection Agency Arsenic Demonstration Project, Round 1. Climax has two 140-foot deep wells. The wells have a flow capacity of 140 gallons per minute and 160 gallons per minute. However, only one well is operated at any one time, with the two wells alternating on a monthly basis. The wells have about 35 micrograms per liter of arsenic, primarily arsenic 3, and 0.5 milligrams per liter iron. This represents an iron to arsenic ratio of less than 20:1, the ratio needed for efficient arsenic removal. The demonstration project added a skid-mounted system of 2 coagulation contact tanks and 2 pressure filtration tanks. The major components in the treatment process are pre-chlorination. The original gas chlorination system was replaced with a liquid chlorine feed system to improve the reliability and safety of the chlorination system. This converts the arsenic 3 to arsenic 5 and provides the oxidation of the natural and added iron, ferric chloride. Coagulation. Ferric chloride is added to the water at a dose of 1.2 to 1.3 milligrams per liter. 2 345-gallon, 42-inch diameter, 72-inch tall fiberglass contact tanks that are typically operated in parallel provide 5 minutes of contact time to allow the formation of iron flux and arsenic adsorption prior to filtration. Filtration. 2 pressure filters are arranged in parallel. These filtration vessels are 36 inches in diameter and 72 inches tall. Each vessel is filled with about 24 inches of macrolite media. This media is a 40-60 mesh ceramic-based media. The macrolite is underlined by 1 inch of garnet sand over a slotted stainless steel underdrain. Flow is controlled through the filters to 70 gallons per minute each, using flow-limiting devices. Automation. The system is fully automated with an operator interface, programmable logic controller, and modem housed in a central control panel. The filters are operated at a rate of 10 gallons per minute. The pressure drop across the filters is about 15 psi. The filters are automatically backwashed at a pressure drop of 25 to 30 psi. The backwash includes an air sparge, brief settling, and a hydraulic wash at a flow rate of about 55 gallons per minute.
Well, the backwash starts out, it drains the tank down a little bit, and then it air sparges. And the idea of that is to stir the stuff up and kind of rub the grains together to break the stuff off. And then that settles for 5 minutes, and then it goes into a backwash for 10 minutes.
The filter-to-waste process is used for about 5 minutes prior to being returned to service. The backwash cycle is accomplished on only one filter at a time.
You know, chances are when we're making backwashes, we lose a little bit of a media. And all we have to do is just add media to it.
The backwash water is discharged to the sanitary sewer via a newly constructed lift station. The plant produces a finished water arsenic concentration of 5 micrograms per liter or less. an adequate margin below the new MCL of 10 micrograms per liter. Even though the system had no treatment other than chlorination prior to the demonstration project, the operator indicates that the process is easy to operate.
Yeah, it is. It's the simplest one that we looked at.
The operator runs the system on a part-time basis. For more information on these and other EPA arsenic treatment technology demonstration sites, you can visit EPA's website at the address shown on the screen.